In this question, we want to use the graph to discuss the continuity of the function, state the interval where the function is continuous, and whether the discontinuities are removable or non-removable. So on this question, we have a couple blanks to fill in. We want to state where the discontinuity is, what type that discontinuity is, whether it's removable or non-removable, and then also state the interval in which the function is continuous. So when you're visually looking for continuity, what you're looking for is to be able to draw the graph without picking your pencil up off the paper. So you can see that along this section, I would be able to draw that line without picking my pencil up. And so this portion is continuous. And then along with this line as well, this portion is continuous. The only point where we have to pick up our pencil is that break that is in between those two lines. And that break occurs at an x value of 2. So we have a discontinuity at x equals 2. And this is a non-removable discontinuity. Let me spend a little bit more time on the difference between removable and non-removable. So when a function has a removable discontinuity, what that means is that the discontinuity is basically a gap of a single point, meaning that if you were able to fill in that one point, then the function would be continuous. So you see a removable discontinuity on graphs where maybe you have a parabola and a single point in that parabola is gone. So you have like an open circle at that spot. So this is a discontinuity because you would have to pick up your pencil. You'd be able to continuously draw this side, and you're able to continuously draw this side, but you have to pick up your pencil between them. But that gap that you have is a gap of a single point. So I could make this function continuous by filling in that single point, versus this particular gap is more than a single point. So it would take more than a single point to connect these two lines together, and that's what makes this a non-removable discontinuity. So we only have a discontinuity at this one x value. The function is continuous for all other x values. So we're going to be able to say that the function is continuous on the left. That goes from negative infinity all the way up to 2. And it's continuous on the right, which starts at 2 and goes to infinity. So this function is continuous from negative infinity to 2, union with 2 to infinity. And I have to pause here because I actually misstated there a little bit, because we can also consider what's called one-sided continuity. And one-sided continuity, that's when for your continuity criteria, you have 3 criteria. F at the value needs to be defined. The limit has to exist. So the limit as x approaches c of our function has to exist, and they have to agree with each other. So that means that the function value has to equal the limit value. So on this example here, where we have a discontinuity at 2, we can see if there's one-sided continuity. And so on this side, because of that open circle, f of c is not defined. So it doesn't meet the criteria. But on the other side, because of the filled-in dot, f of c is defined. And instead of looking at the overall limit, we can look at the one-sided limit just from above, and these two match each other. The function value and the limit value match each other. So because of that closed circle there, we actually have one-sided continuity, and we can change this to a bracket instead of a parenthesis. So when we use that bracket, we have that special one-sided continuity when we're only looking at one side of the limit with our continuity criteria. Now on this question, we're given a function f of x equals 2x cubed minus 5x squared minus 4x plus 3. And we want to find the values of x that have horizontal tangent lines. Now the significance of looking for horizontal tangent lines is that a horizontal line has a slope that is 0. So the slope is 0. Now a function is going to tell us the slope if we look at the derivative of that function. So the derivative is going to tell us the slope at any point on that function. So what I want to do to find any horizontal tangent lines is to calculate the derivative and then set that derivative equal to 0. The derivative represents slope, and a horizontal line has a slope of 0. So I'll set that equal to 0 and solve. So let's calculate the derivative of this function. The derivative of 2x cubed, 2 is a constant multiple, I'll carry that down. On x cubed, I'll use the power rule, that's 3x squared. 5 is a constant multiple, I carry it down. Derivative of x squared is 2x using the power rule. The derivative of negative 4x is negative 4, and the derivative of a constant is 0. So we've calculated this derivative to be 6x squared minus 10x minus 4. So now we'll follow this equation here. We're setting the derivative equal to 0, and we're going to solve this equation. So we have a greatest common factor of 2. If I factor that out, I'll have 3x squared minus 5x minus 2. And I'm going to try to factor this into 3x and x. I could use a 2 and a 1. That would give me 1 and 6. I need a negative 6 and a positive 1, and that will give me the negative 5 in the middle. So once I have it factored, I'll set each factor equal to 0 and solve. I'll subtract 1 on both sides. That gives me 3x equals negative 1. Divide by 3, and x equals negative 1/3. Over here, I add 2 to both sides and get x equals 2. So this function will have horizontal tangent lines when x is equal to 2 and x is equal to negative 1/3. Let's confirm this with a calculator. So I get my calculator out, and in my y equals menu, I'll type the function 2x cubed minus 5x squared minus 4x plus 3. We'll take a look at the graph, and maybe we'll take a screenshot of this graph so we can draw on it. What you'll notice about this graph is that at x equals 2, which is right here, you can see this little dip in the graph, and we would have a horizontal tangent line at that point. And then we have a little peak over here, and that's going to probably be at negative 1/3. And at that point, we have another horizontal tangent line. Along this side here, all the tangent lines have a positive slope, and it starts turning. We get to flat. On this side, we have tangent lines that are negative slope, and it starts turning and becomes flat. Positive tangent lines here. So we have found the two places where this function has horizontal tangent lines at x equals 2 and x equals negative 1/3. For this question, we want to discuss the continuity of the function, state the interval where the function is continuous, and whether the discontinuities are removable or non-removable. And this time we have a piecewise defined function, that's f of x equals 3x minus 4 when x is not equal to 1, and 2 when x equals 1. So first I'm going to start thinking about these individual equations here. We have y equals 3x minus 4. That is a linear equation, which is a type of polynomial. And these types of equations don't have any discontinuities. So this is an equation that is continuous over all real numbers. The second equation, y equals 2, is a horizontal line. It's also a linear equation, which is a polynomial and has a domain of all real numbers and is continuous on all real numbers. So for this piecewise defined function, we really need to just pay attention to where these two functions are being pieced together, where they're being joined together, to see if it is a continuous function. So we need to focus in on x equals 1 to decide if the function is continuous at that point. We need to know continuous at x equals 1. We're going to put question mark. So there are 3 criteria for a function being continuous at a point. You need the function to be defined. You need the limit to exist. And you need for the function value and the limit value to agree. So you need the function value to equal the limit value. These are the 3 criteria. So we're going to check those 3 criteria. So the first one, f of 1 being defined. F of 1 is defined. We use the second equation whenever x equals 1. And f of 1 is going to equal 2. And then we need to decide if the limit exists. So when we're deciding if the limit exists, we're going to look at the one-sided limits. We're going to look at the limit as x approaches 1 from above, and the limit when x approaches 1 from below. So this is going to tell me which equation to use to find this limit. X approaches 1 from above. So I look at my rules over here, my conditions. Here are the conditions. I use the first equation whenever x is not equal to 1. I use the second equation whenever x is equal to 1. So this is telling me that x is going to be more than 1. More than 1 is not equal to 1. So I'm going to use the first equation to answer this limit. It's going to be 3 times 1 minus 4. That's 3 minus 4 is negative 1. So I got the limit from below being negative 1. Then I'm sorry, that's the limit from above. Then I'm going to find the limit from below. We want to find x approaching 1 from below. Well, below 1 is less than 1, and less than 1 is not equal to 1. So once again, we're going to use the first equation to answer this limit. 3 times 1 minus 4, that's 3 minus 4 is negative 1. So we've got the limit from below being negative 1, the limit from above being negative 1. So the overall limit is negative 1. So for our second criteria, remember this was our first criteria, our second criteria, we did find that the limit exists. The limit as x approaches 1 of f of x is negative 1. The final criteria is that the two agree with each other. The function value equals the limit value. So the limit as x approaches 1 of f of x, we found that to be negative 1. The function value at 1, we got that to be positive 1, or sorry, we got that to be 2, and those are not equal to each other. So our third criteria for continuity has failed. This function is not continuous at x equals 1 because of that third criteria. So we do have a discontinuity. There's a discontinuity at x equals 1. This discontinuity will be removable. And the reason why it's removable is because if we just change this one value, this 1 point is the problem. That 1 point, if we move it to be negative 1. If we move that 1 point to be negative 1, then the continuity criteria would be met and this function would be continuous. So removable discontinuity is if you change a single point, then it becomes continuous. So that's a removable discontinuity. And then finally, we want to state the interval where the function is continuous. We only found this one discontinuity, so the function will be continuous everywhere else. It's going to be continuous from negative infinity to 1 union with 1 to infinity. Thank you for checking out my videos. Have a great day.